Okay, welcome back everybody. So this would be our last video of that first course, that first one credit course on groundwater cycle. The last video was a bit long because there was a lot of information on hydraulic conductivity and heterogeneity and anisotropy. And today is sort of our final lecture, and we're looking at solutions of the groundwater flow equation. So again, this is going to be a longer lecture that sort of is, really wrapping up what we've done so far and looking at, what we can do with all those equations. Now that we have all the different cases, how do we really use it in engineering and practically? So here's an example of a simulation. So basically what we'll do today is look at the flow equation and solve it with finite differences. And this is really the standard way of doing it in industry. And you can see here on the right-hand side an example of a domain where you can see a heterogeneous formation, different types of things, right? Alluvium, different types of alluvia, different types of rocks, so on and so forth. So all those things would have different hydraulic conductivities, obviously. And the way we do it, we solve those equations on grids, basically. So today I'll do a very brief introduction to finite difference methods, and I'll show you in Excel how you can implement those solutions for the cases we've seen so far, and that leads us to basically professional software that are used in industry that use exactly the same methods, except of course they have wrappers, so you don't really see the equations, you just see the buttons and choose, install your domains and so on. But this is what the engine in the background is. And really this is all it is. This is finite difference methods right here. So on the right hand side we have the differential equation like we've seen in the math so far. So some function of x, right, df dx, the first derivative of x is really, so the differential form of this can be approximated by that difference equation here, that is the function at some small distance away minus the function at some small distance before, divided by twice delta x. And on the left hand side here, that graph shows you why that is, right? So let's say we want to approximate the differential df dx of that function f of x here, right? So we know that df dx is basically the slope or the tangent here of the function at that point. Okay, so this is just from remembering our basic math here. You can see here, if I take a parallel to that slope, to that tangent, right, we can approximate that slope by dy dx, right, dy dx or df dx, right? So the y here, so if I go a little bit, after x, again, this is x, this is f of x. If I go x plus dx, x minus dx, right, and I approximate, I look at my function at those places, right, the slope here, dy dx, if you look at dy dx, it is literally f plus delta x minus f x minus here, right? This is my dy, and my dx here is 2 times delta x, right? X plus x minus, so this is 2 times delta x. And this is the finite difference approximation. So the approximation of my differential form is that difference equation. Now, how does that work? So before I actually go on to tell you how that works, so this is the one we've just seen graphically, right? Now we also need the second differential, right? We remember from the Boussinesq equation, or all the equations we've used, all of them are d squared h dx squared, basically. So it's a second differential. Now how does that work? Well, so the theory behind it, and again, there's a lot, we could do a whole course basically on those, but it comes from Taylor series expansion. And again, I put the formula here. You don't have to worry too much about, what it is, but just for completeness, this is the equation for the Taylor series expansion. And if you expand the function f at some location, x plus dx at some point a at x plus dx, you can see that if you plug in, you get the function at, so again, I called it I plus 1 here. You get f of I, fi plus df dx dx plus the second differential dx squared over 2 factorial, and again, that comes from here. So this is the first derivative, n is 1. This is the second derivative, n is 2. And then some error, right, order third derivative. So this is just an error, we don't care. If we look at the place right before, x minus dx, right, now this business here is going to become x minus dx. So minus to the 1 is minus. So the only difference here is that minus in that first term, right? Now if we do, if we subtract these two equations, so if I do I minus 1 minus f at I plus 1, right? If I subtract those two things, those two equations, you can see that these are going to disappear. Now this minus that is going to be a 2, so now we have minus 2 of those, right? 2 of those, that's where that 2 come from, so on and so forth. So if we replace in, if we subtract those two equations, we end up with the exact same as I explained graphically before. Now if we add them up, finally we get, again, if we subtract them, obviously those disappear, right? Because this is plus 1 minus 1 of those, they're gone. Now if we add them, obviously the first derivative are going to disappear because there's a minus, right? So plus, minus, minus, so those two disappear and we're left with the second derivative, and now we can expand the second derivative here and have an expression for it. Okay, and now my battery is going to die, so I'm going to change it, and I'll continue right after a second.